Okay. Yeah. So the question in chat was what the deal with final is. I'll make an announcement over the weekend. And and tell you all like specific dates. But I think our final. Actually, I can look right now. I think our final is scheduled for like the 21st or something. Um, Let me see here. UMD final exam schedule. What? Okay. So this is if course meets Monday, Wednesday, Friday at what? This course meets at 1. So Monday, Wednesday, Friday at 1. Exam will be on Thursday, December 17th. From 1:30 to 3:30. Well, that doesn't mean anything. So the final exam I guess is scheduled for the 17th, which means that I will post it a few days before that. So I'll post it a few days before that. Maybe like I'll post it on like the 14th or something, which is our last day of classes. Um, so anyway, yeah, that's the deal. So I'll post it like the 14th ish. You'll have a couple days. You'll have like 2.5, 3 days to work on it, and it'll be due midnight on that Thursday. Uh, let's see. Well, it's early, so actually I'm gonna do it another way. That way you don't have to like technically start working on it before finals. So rather than that, since it's early in the schedule, I'll post it on that Thursday, and then you all can turn it in. Like, actually, no, I don't like that either, because it's a conundrum because normally, right, you would be done with this course as of that Thursday. So the options are that I could either assign it basically that day, and I wouldn't make it as long if I gave you multiple, like if I gave you a single day rather than multiple days, and then have it due also that day. That's possible. Because if I put it up earlier, then technically I guess I'm having you work on it before. I guess there's nothing wrong with that though. I don't like extending your schedule, right? Because like if this is according to your final schedules, if this is your last class, then me assigning the final on the 17th and having it due like the 19th or 20th, that's like extending your semester by 3 days. And yeah, it's cumulative. It's cumulative final. Um, hmm, hmm. I think what I will do is I'll I'll assign it early. So I'll put the final exam up on like not this coming Monday, but the Monday after. And then it will be due either midnight on Thursday or yeah. I mean, it'll be due midnight on Thursday, or maybe I'll make it due the. Actually, yeah, midnight on Thursday is fine. Yeah, that's fine. So that's what I will do, and it will be of a length that you can finish it in, like I don't know, in like an hour and a half if you sit down and work on it. So it's plenty of time for you to pick some time during, even if you didn't get to work on it until Thursday, that's plenty of time. So really, I'm just giving you extra time that you are in no way required to make use of. Um, so that's what I'll do. So I'll put it up on Monday, and then and then it'll be due that Thursday, and that way I don't do anything stupid where like according to this you should be done with this course by that Thursday, so I don't want it to extend longer than that. So anyway, that's what I'll do, and I'll put that into writing in an announcement sometime this weekend to let you guys know. So yeah, so now you all have you have been witness to the real time decision making, uh, you know, process. So that's how I decided. Okay, so that's the deal. All right. So we have one more thing that is going to come to us from the textbook, and while it would be interesting to go into the Chapter 8 stuff, which is the geometry of vector spaces, which is really, really interesting and something I'm definitely into because I'm a geometer. But I think what would make more sense rather than do that is to bring in some topics, like I said, that I think are interesting. One, there's something that the textbook doesn't cover, but it's technically in the course description of this in the course catalog, which is Jordan canonical form. So I will talk about Jordan normal form on Monday. I think, and then after that I'll spend one day on like the Hadamard matrix conjecture, and then the last two lectures you can just ask me questions. Basically, they'll be glorified office hours. So I think that's the plan. Okay, so like I said, one more thing that we want to discuss, which is the singular value decomposition. So this, for the purpose of applications, this is actually one of the more useful things. I mean, okay, so like clearly the basic stuff that you do in linear algebra is the stuff that gets used all the time. So I'm not, that's the stuff going on constantly. But in terms of the named things that are used, singular value decomposition is probably one of the most important ones. So this has a ridiculously long list of applications. I think I told you last time that if you look at the Math 401 notes, which are freely available online, that covers all the topics that are covered in Math 401. So Math 401 is it's applications of linear algebra, which is basically a long list of some topics are related, many are it's just kind of a list of not random topics, but like marginally related, somewhat related, and then unrelated topics that are basically just trying to give you a broad overview of like all the possible, applications of linear algebra. SVD, singular value decomposition, is used in like, off the top of my head, I'm going to estimate about 30% of the applications just are direct applications of the SVD. So singular value decomposition is really, really important, and you'll see why it's important when I write out the intuition here. So when we diagonalized a matrix, okay, we took matrix A and we wrote it as PD, P inverse, where P is some invertible matrix and D is a diagonal matrix, right? But this clearly only worked when A was A needed to be a square matrix for us to even talk about this. Okay, but it turns out that even when A is an M by N matrix, there is a factorization that can be done that is A is Q D P inverse, where the Q and the P satisfy some things. Okay, this is actually pretty amazing. Okay, one example of something like this is called the singular value decomposition. Okay, so the singular value decomposition is one of these examples. What is the intuition behind it? Before I even define the singular value decomposition, what is the intuition here? Okay, maybe I'll write that out. What is the intuition here? So what line of thinking that would naturally arise would lead you to coming up with the SVD? The key thing at play here is the fact that there was an interpretation of just the usual diagonalization that is kind of hidden. And the reason that it's hidden is because we were focused on the fact that, yeah, you could like diagonalize a matrix and it made iterated matrix multiplication really easy. And of course it in a sense you could basically change coordinates. So given a diagonalizable matrix, you could change coordinates to a basis where that matrix that you were dealing with was a diagonal matrix, which is like the easiest thing to deal with. So that's what we were mostly focused on. But it turns out hiding in all that is another property that can be overlooked easily. So if A, let's say that if A is a symmetric matrix, let's say that let A be a symmetric matrix, then its eigenvalues measure the amounts that A stretches or shrinks certain vectors. These are the eigenvectors. Right. We phrase this as on the eigenvectors, the matrix was acting like multiplication, right? It was literally scaling it by some scalar. That scalar for those vectors was the eigenvalue. Okay. All right. Okay. So to see this, right, if we have an eigenvector x for some associated some eigenvalue lambda, and we're dealing with a unit eigenvector, then if you compute the length of ax, well, that's the length of lambda x, but then that's the absolute value of lambda times the length of x, but length of x is 1, so this is just absolute value of lambda, right? So if we have arranged that the eigenvalues for A are listed out as, lambda 1, lambda 2, lambda 3, with lambda 1 being the biggest, right? So we did this in the last section. We were talking about constrained optimization, because it was useful there for identifying maximums and minimums, because that would be at the other end, right? Not just having them be strewn about in any order. You will see why it's going to be important here, because if lambda sub 1 is the greatest eigenvalue of A, right, that is the eigenvalue with the greatest magnitude here, right? Then, so here, I guess greatest eigenvalue is a little bit misleading here. Okay, so what we want here is with greatest magnitude. Okay, because if we're speaking in absolute terms, then you could have a negative eigenvalue here that had larger magnitude than another, and what I'm going to say here would be true for the negative eigenvalue, not necessarily the positive one that's greatest. And so then V1 which is an eigenvector associated to lambda 1, identifies a direction in which the stretching effects of A is greatest. Okay. Okay. Now, thinking about this in terms of stretching a length or maximizing a length, right? So we could formulate the same sentence with using the word maximize here. Um, this is useful for various things. In fact, thinking about it this way also allows us to identify what I think is one of the coolest applications of SVD, which is an image compression. So it turns out that, of course, I haven't said anything about the SVD yet. This is just the setup of what we already know for square matrix and eigenvalues and eigenvectors. But for an SVD, it is going to involve these things called singular values that are going to play the role of the eigenvalues. Okay, so these singular values are going to play the role of these eigenvalues. And in this way, they are going to do a similar thing that these eigenvalues are doing in this example, where the largest one, or the one of largest magnitude, is telling me the direction in which this distortion in some way is the greatest. In the context of image compression or data storage, this is basically telling me where most of the goods are in like a block of data. Okay, and so for instance, an application of this, and you can see examples of this in the Math 401 notes, and maybe I'll put out an announcement that gives you a link to the Math 401 notes if you wanted to actually have a look at some of those examples, because there's some really good ones of image compression where you have an image, and for space reasons you want to toss out some data in that image so that it is easier to store, right? It's a smaller image. But of course, if you just randomly toss out blocks of data from an image, you're going to severely degrade the quality of the image typically, right? One, I mean, you might end up with something that's just not accurate at all, right? Depending on what you toss out. So the idea here is if you're trying to compress an image, you want to toss out the right stuff, right? You want to toss out the stuff that means the least. Okay, because I mean, in terms of size, right? Like if I have two blocks of data, and one is essentially like meaningless, superfluous data, but the other is like everything I need, right? Or maybe the other block is redundant or something. Then I mean, if they have like the same size, well then like it doesn't matter. It's a matter of which one is important, right? If I can toss out something that has the same size and actually doesn't degrade the amount of data that I have, that's great. And so the idea is that the SVD actually identifies in the same way that here you're identifying a direction of maximal stretch. In the context of image compression, you're identifying chunks of data where most of the goods are. So in order to maintain like the highest quality of your image while tossing out a huge amount of data, it's the singular values and the SVD that allows you to do this. And so in some cases you can, drastically reduce the size of an image while keeping it like almost identical in image quality. So that's like one of the coolest examples of using SVD. Anyway. So this is all stuff that we have that we've seen before, just kind of recast in another way. And so I'm not actually going to go through this example, but here's a quick example of that that we can have a look at. So let's say I have rectangular matrix A, and you have linear transformation that just multiplies a vector by A. This takes unit sphere in R3 onto an ellipse. Okay, and then you're asked to find a unit vector at which this length is maximized and compute this maximum length. Okay, so this is the question that you're asked here. And in order to do this, you'll see that what is actually done is should I do this out or should I? Let's see here. Can I do this example out? No, I don't think I'm going to because what we get to next is more important. So anyway, in order to do this, so you're asked to maximize the length of AX. So that's the same thing as maximizing the length of AX squared. This is typical what you do in vector calculations, because length of a vector is nasty, but length of a vector squared is easier to deal with. If you're maximizing length of a vector, the square of the length is also maximized. So we can look at the square of the length maximized instead. But the square of the length here, of course, can be written in this way. But written in this way, I get this quadratic form because A transpose A is symmetric. Okay. Why is A transpose A symmetric? Because if you transpose A, you get A transpose A. So it's equal to its own transpose. So A transpose A is always symmetric. So I have X transpose times a matrix times X. That matrix is symmetric. So this is a quadratic form. Okay, and this is a quadratic form subject to this constraint that I'm dealing with unit vectors here, because I'm mapping, all these are mapped from the unit sphere in R3. All right, so all these vectors X have length 1. And so I'm in the case of a quadratic form subject to a constraint, which we just did, right, last lecture. Okay, and so the maximum value of that is the greatest eigenvalue of A transpose A. Right? Therefore, the maximum value is attained at the unit eigenvector of A transpose A corresponding to lambda 1, and that's how this is computed. Okay. Similarly, you can compute the other eigenvectors, and those would be, those. Well, you can check that the other eigenvalues are going to give you directions in which that stretching is smaller. Okay, and so you can actually compute the maximum value by just evaluating it on that unit eigenvector. Okay, now again, what we did there is we started, maybe I'll go back. So we started with a matrix that was not square. This matrix is not square, right? But in asking this question about maximizing this length, we looked at this quantity that involved a matrix A transpose A, and even though A itself was not square, A transpose A is. Not only is it square, it's automatically symmetric. Okay, and so even though our original question was a question about a rectangular matrix and its effects on some unit vectors, in actually computing this stuff, the matrices we were dealing with were not rectangular, right? We got a square matrix out of that and did some analysis. So now the big obstruction to using this analysis for a rectangular matrix is that a rectangular matrix has no eigenvalues. Right? It does not have eigenvalues. Okay, well that seems really rough for us, because we needed the eigenvalues specifically for finding these maxima and minima, right? That was required, right? They were corresponding to those things. So this seems like a really big problem. And there's no fixing it, because we know the way eigenvalues are defined. They're roots of characteristic polynomial, but characteristic polynomial involves a determinant, and determinants only make sense for square matrices. So there's really no fixing this. Okay, these are never going to have eigenvalues, but they have things that play the role of eigenvalues. Okay, but they have quantities that play the role of eigenvalues. Not perfectly. these quantities are called singular values. Okay. So these quantities that I'm alluding to are called singular values. And so we need to talk about the singular values of a rectangular matrix. Okay. So the singular values are in correspondence with the eigenvalues for a matrix if the matrix in question is actually square. Okay, but in general, if it is not square, if it's rectangular, then where do I get these singular values? So we have a matrix A. It's an m by n matrix. Okay, then regardless of what kind of matrix this is, I have an m by n matrix with real entries. A transpose A is symmetric. Right, so this is symmetric always. Well, we've seen that symmetric matrices are about as nice as possible, right? They basically every property you might want them to have, they have. They can be orthogonally diagonalized, which automatically gives you a ton of other stuff. We already know that they have nothing but real eigenvalues. The eigenspaces in question have a nice property because they can be orthogonally diagonalized. So lots of good stuff comes from this. Thus, they can be orthogonally diagonalized, or thus it can be orthogonally diagonalized. Okay, so let V1 to Vn be one of these orthonormal bases. So let V1 to Vn be an orthonormal basis for Rn consisting of eigenvectors. So these are eigenvectors, not of A, because A doesn't have eigenvectors. They're eigenvectors of A transpose A. Okay. Let lambda 1 to lambda n be the associated eigenvalues. Again, eigenvalues of A transpose A, because A itself does not have eigenvalues. Okay. Then, for I between 1 and n, if I compute the length of the vector a v sub I squared, what do I get? Well, just by definition of the length squared, this is a v sub I transpose times a v sub I, which of course is v sub I transpose a v sub I. But this v sub I is an eigenvector, right? So what do I get out of this? Well, this is an eigenvector of A transpose A. So if I think of associating in this way, right, what do I get here? By the eigenvalue eigenvector definition, this is v sub I transpose times lambda sub I v sub I. Right? And that's because lambda sub I is an eigenvalue associated eigenvector v sub I for A transpose A. Okay, and thus this is, of course, just lambda sub I, right, since v sub I is a unit vector. And so the length of a v sub I is, the length of a v sub I squared is lambda sub I, right? Okay, So thus, our eigenvalues are all non-negative. And thus we can arrange them in such a way that we can arrange them as lambda sub 1 is, we'll label that to be the biggest, right? And that's greater than or equal to lambda sub 2, greater than or equal to lambda sub 3, and so on, all the way to lambda sub n, and this is non-negative. Okay. All right, so we're almost there. So then the singular values of A, right, these eigenvalues, of course, are eigenvalues of A transpose A. So the singular values of A are the square roots of the eigenvalues. So these are sigma sub I, which are defined to be the square root of the lambda sub i's. Okay. I.e. the square roots of the eigenvalues of A transpose A. Okay. Sigma is used here because sigma is the Greek letter S, so, and we're talking about singular values, so these are sigma sub i's. They're the square roots of these eigenvalues of A transpose A. Okay. Another way of thinking about this, I'll bring some of those things back here in a second. Also, note the singular values, the singular values of A are the lengths of the vectors AV1, AV2, and so on. Where does that come from? Let's go back here. When we did this computation, we found that each of these eigenvalues of A transpose A is actually equal to the length of A V sub I squared. And so if I take the square root of both sides, of course, the singular value sigma sub I is equal to the length of A V sub I squared. So what does this mean? This means that you have a matrix A, right, that's rectangular. You look at A transpose A. You find the eigenvalues and eigenvectors of A transpose A. Once you found a list of eigenvectors, you look at the length of A applied to a unit eigenvector. That is a singular value for A. Okay, that's another way of viewing this. It's not that A transpose A equals lambda. So I got a question in the chat that's asking this step. So it's not that A transpose A equals lambda I. It's that A transpose A VI equals lambda VI. And this is just the eigenvalue eigenvector definition, right? So if you have a matrix B and an eigenvector eigenvalue, eigenpair for B, then BV is equal to lambda V, right? That's the definition of eigenvalue eigenvector. So in this case, B is A transpose A, and lambda is lambda. Yeah. So that's why that works. So yeah, this is the definition of eigenvalue eigenvector. Okay. So this is nice. Now I have a couple facts here to mention before. Actually, I have one fact to mention, then I'll lay out the SVD. So theorem. So suppose we have a set V1 to Vn as above. That is, they're an orthonormal basis of Rn consisting of eigenvectors of A transpose A arranged in the usual way. Okay, maybe I have to write that out. So orthonormal basis of Rn consisting of eigenvectors of A transpose A arranged with corresponding eigenvalues listed in decreasing order. So lambda sub 1 is greater than or equal to lambda sub 2, and so on, all the way down to lambda sub n, which is guaranteed to be non-negative. Okay. And suppose, I put this in parentheses, so I guess I need to close my parentheses. And suppose A has R non-zero singular values, right? Because these singular values are defined to be square roots. So, and of course, there's square roots of eigenvalues, sorry. And of course, we know it's very possible for a matrix to have zero eigenvalues. So, so you know, some of these singular values could be zero if they're associated to a zero eigenvalue in A transpose A. Okay, so suppose it has R non-zero singular values, then the set of vectors AV1 to AVR is an orthogonal basis for the column space of A. And the rank of A is equal to R. Okay. Okay. Now, you might say, wait, like it has R non-zero singular values, so then how do I know that the first R of these vectors provide an orthogonal basis? Remember, because that's why I included this zero here, even though it's not stated in the textbook. Because remember, because of this fact, once you hit zero, the rest of them are zero, right? So if there's any singular values, you have arranged your eigenvalues of A transpose A like this. Once you hit an eigenvalue 0, well, then the rest past that point are 0. So then when you say that it has R non-zero singular values, it means that the first R eigenvalues associated to A transpose A are non-zero. So that's what's being said there. So that's why you don't have to worry about anything when it comes to that. So then this set up to R, this is an orthogonal basis for the column space of A, and the rank of A is actually R. So the rank of A is the number of non-zero singular values. Okay. All right. And so this allows us immediately to bring up the singular value decomposition. Okay, so I need one more thing first. Okay, so I have a definition. If A is m by n, I want to form, let sigma be the m by n diagonal in quotation matrix. That is, sigma is a matrix that has another matrix D in this block, and then it looks like this. Okay. Now, how many rows does this thing have? It has m minus r rows, right, of 0. Oh, I did a bad job pointing to the here. I'll circle. You have m minus r rows of zeros, and how many columns of zeros do you need here? N minus r. Right. So from this, if you want sigma to be m by n, and it has n minus r columns of zeros and n minus r rows of zeros, then what size does D have to be? All right, so D is an R by R diagonal matrix. That looks suspicious. Oh, so Gustavo asked, can we have negative eigenvalues? Not for this type of matrix, right? So if you go back to A transpose A, you can't have negative eigenvalues because every eigenvalue is a length squared, right? Lambda I is some length squared. So that was the purpose of writing this out, because I have this statement here, thus our eigenvalues are all non-negative. Right? So I can't have any negative eigenvalues for an A transpose A. So A transpose A is a special beast. Okay, so this matrix is always guaranteed to have non-negative eigenvalues. They can be zero, though. They can be zero. Okay. All right, and so this R by R matrix is a diagonal matrix. If I don't tell you anything else, just based on what I've written so far, what do you think that diagonal matrix D is going to have on its diagonal? It's an R by R diagonal matrix. That's a very suspicious size, given what I just defined R to be up here. Right? It's going to have the R non-zero singular values on it. Right? And so this D is going to play the role of the diagonal matrix D from our diagonalization before. Yeah, it's going to have the singular values. So in the chat, yeah, the singular values are going to be on D, or on the diagonal of D. Okay? All right. And so what is the statement of the singular value decomposition? So theorem. This is the singular value decomposition. Oh. Okay. So let A be an m by n matrix with rank R. So let this matrix A have rank R. Then there exists an m by n matrix sigma as before, for which the diagonal entries in D, which is an R by R matrix, are the first R singular values of A. So we have singular values arranged in the same way that the corresponding eigenvalues for A transpose A are arranged. So these are all, actually, these are strictly greater than 0, right? Because we're tossing out the 0 ones. So all of these as square roots of positive numbers are positive. Okay, and there exists an m by n orthogonal matrix U, and an n by n orthogonal matrix V such that A is equal to U sigma V transpose. This is the singular value decomposition. Okay. Abbreviated frequently as SVD because it's kind of a mouthful. Okay. Now, I said the, but actually this is not unique. So U and V are not uniquely determined. So this is technically a singular value decomposition. There's several, but anything that is of this form is called a singular value decomposition of A. So this form is the singular value decomposition of A. Okay, the columns of U are the left singular vectors, and the columns of V are the right singular vectors. Okay, so columns of U are left singular vectors. And the columns of V are right singular vectors. Now, there's a lot of tricks that go into using this, because you might look at this and you say, okay, wait, like what, how do I make this work? So the vectors V, so constructing V and U it's straightforward, but it is typically annoying. And the good news is that for the most part, for a lot of the applications, you can shorten what needs to be done. There's some shortcuts that you can use here. Okay, so I am close to time though, so maybe what I think I'll do next time is do an example of SVD stuff. Might do one example from the textbook, and then I think the more interesting examples are the application examples that you might see in a course like Math 401. So I think I'll include a couple of those. So I think I might talk about the image compression example. So I'll do that next time, and then I'll introduce the Jordan canonical form. And that should finish up Monday's class. Wednesday I'll do Hadamard matrix conjecture. And then, like I said, we'll have 2 free days where you can just ask a bunch of questions, and that will be the course. So we've basically finished everything that's coming from the textbook this semester. Evan, yeah, so I'll talk a little bit more about that. So Evan asked, are there any notable features of left versus right singular vectors of geometric interpretation? So I'll talk a little bit about that next time when I do an actual example of this stuff. All right, so yeah, I'll talk about that on Monday. All right. So anyway, you have, let's see, what do you have? You have, I think I decided no more homeworks because you're already, like, the bit that you haven't been tested on, you're going to be tested on that on the final anyway. It didn't really make that much sense to give you another homework. You already have a MATLAB project that's due at the end of class, so I think that's it. All right. So anyway, I will see you all on Monday.